Alright, ladies and gentlemen, so here is a PowerPoint on naming chemical compounds, and has the subtitle there that I must be the weird one, because when I went through naming chemical compounds many, many years ago, it was one of the easiest things in chemistry that I can remember. Now, I thought that meant that it was an easy concept to get, but judging from the difficulties that both you guys as AP chemistry students and general chemistry students have had with naming chemical compounds in the past, I've finally come to the realization that maybe it's just hard and I need to spend a little bit more time on it. So that's what we're going to be doing here with this PowerPoint. Um, yeah, here we go. First of all, we have the three different things that we're going to be looking at: the ionic compounds, covalent compounds, and acids. Make sure that you can identify what compound is what. If you can't, you will name it incorrectly. Even if you know all of the rules for each of the three different kinds of compounds, if you identify it as something it's not, you're going to run into problems. So how do I identify them? If the compound contains a metal, it's ionic. Period. If the compound contains a polyatomic ion, it's ionic. For example, that phosphate ion there with the -3 charge, if that's in it, it's ionic. If all it has is two nonmetals, it's covalent. And finally, if the compound begins with a hydrogen, it's an acid. Now, it's always important to say that there are always exceptions to these rules. This is something that will come up very commonly in chemistry for the rest of the year. We give these rules and say, but wait, there are exceptions, and then we identify those later. For right now, these are the things that you need to be able to do to identify the difference between ionic, covalent, and acids. So again, a periodic table here. This will pop up several times during the PowerPoint so I can show you. Over here, these are the metals. Here, more metals. Aluminum, a metal. Here's some metals down here too. Bismuth, and lead. All of those are metals. If it contains one of those things, it's ionic. The non-metals are here, from carbon to fluorine down to iodine. We have selenium and phosphorus and sulfur. So not very many non-metals here. So we have a lot less covalent molecules to name than we do ionic. We're going to start with the ionic then, because that's the biggest thing. Those contains the most differences and is the most difficult. So here we go. Make sure that you understand, with ionic compounds, the prefixes never ever get used except when we have hydrates. So we have this barium chloride with this pentahydrate attached to it. If we see water molecules, we use a prefix to identify how many water molecules there are. So this becomes barium chloride pentahydrate. Hydrate means water. Think about getting hydrated after you do a workout or an exercise, something like that, to remind yourself that hydrate means water. Name the cation first and the anion last. So it's just how it's written. The cation will be listed first, the anion is listed last. That's also how you need to write the chemical formulas. The cation gets listed first, which is the positive, the anion last. The overall charge of the chemical compound must be 0. That'll be more important when we write out the actual formulas for the ionic compounds. We have different kinds of ionic compounds, so we'll start with the simplest. This is a binary. 2 elements, and that is it. 1 element from either an alkali metal or alkali earth metal, and 1 anion that's a nonmetal. So we have metal and nonmetal. We have some examples here. So we have sodium chloride, barium chloride, potassium oxide, rubidium nitride, and potassium iodide. Notice that each of these things, the suffix gets changed to "ide." No Roman numeral, because these things come from either group 1 or from group 2. No Roman numeral necessary when they are either an alkali metal or an alkaline earth metal. If we have a transition metal, we need Roman numerals. This is because the transition metals can often form more than one possible cation, possibly +2, possibly +3. We need to identify which one we are dealing with. So we have some examples here. First one is iron 3 chloride. We know this because chlorine is -1. Since chlorine is -1 and there's 3 of them, the single iron cation has to have a +3 charge, so this overall compound gets the charge equal to 0. So iron 3 chloride, cobalt 2 chloride, iron 3 oxide, copper 1 nitride, and then we have vanadium 2 oxide. You have to use the charge of the anion to figure it out. So that's what we're doing here. Since oxygen is a -2 charge, vanadium must be a +2 charge. The two exceptions to the transition metals that get Roman numerals are silver, it's always +1, and zinc, always +2. There are others besides silver and zinc. These are the ones that we deal with. Those are the most common. We won't see any of the other exceptions. So again here, I want to make sure that we identify that for the anions over here, we have the halogens, which form -1 anions when we're dealing with ionic compounds, oxygen and sulfur, -2, nitrogen, -3. We don't talk about the rest of these nonmetals in here because they typically are not used in ionic compounds. Not very often, anyway. The next part then, and the last part of naming these things, is ones that have polyatomic ions in them. If you have not yet made flashcards to memorize all of the polyatomic ions, you're doing it wrong. Get those flashcards made, learn them, memorize them. We'll be using them a lot throughout the year. You have to be able to identify what is what. And there we go. And then all I have to do is name them accordingly. It's just the name that the polyatomic ion is. So if we have something like this sodium and nitrate, it becomes sodium nitrate. That's it. The next one is barium nitrite. Then we have ammonium oxide, because NH4 is ammonium, rubidium phosphate, and then this antimony 5-phosphate. Yes, it is possible for antimony to have a +5 charge. Each phosphate is -3, so that makes a -15 with this 5. So we have to have a +15 from the antimony. Each antimony cation then must be a +5. +5 times 3 makes +15. One of the things that we need to know, though, is that you are only memorizing the base polyatomic ion. You memorize nitrate, and then you can figure out nitrite. Now, we use them enough that you might get those things memorized as well, but this is the method. You have the base polyatomic ion, like chlorate, ClO3, that's memorized. If we add an oxygen to it, to ClO4, that becomes perchlorate. So it becomes per whatever that base is, and it stays 8, so chlorate. If we subtract an oxygen, so we have ClO2, we end up with the suffix ite instead. So we end up with chlorite. And finally, if we subtract 2 different oxygens, it becomes hypo, whatever the base is, ite. So hypochlorite. This can work for things like nitrate, sulfate, iodate, bromate. Any of those that contain an oxygen in them have the ability or have the possibility that this could happen. Notice, though, that each time that an oxygen is changed, it does not change the charge of the overall polyatomic ion. It's -1 every single time. So we have some of these that you can try all together. Here's the list. Pause this video now. Go through these things and come up with the answers. So again, you're pausing this, you're doing the work. Have you paused it yet? All right, here are the answers. You shouldn't be looking at these answers until you have paused it and gone through and gotten all of your own answers. First one is magnesium oxide, aluminum oxide, nickel 3 chloride, silver nitrate, iron 3 sulfite, ammonium sulfate, copper 1 perchlorate. So I'll talk about this one. Perchlorate is ClO4 because ClO3 is chlorate. -1 charge, so copper is +1. Zinc cyanide does not need a Roman numeral because it's one of the 2 exceptions. Calcium hydroxide, lithium carbonate, and then we have barium hypoiodite. This 2 is outside the parentheses. So we have 2 hypoiodites. The IO3 is iodate. We have iodite, hypoiodite. All right. Ionic compounds go in the other direction. So now we have the names, we're coming up with the correct chemical formula. Here's the thing. Every single time you write a chemical formula, the overall charge of the ionic compound must equal 0. So make sure you know how to find these charges. Make sure you have your polyatomic ions memorized. And again, this periodic table. We have +1 from the alkali metals when forming ionic compounds, +2 from the alkaline earth, Then again, we go over here and -1 down to iodine, sulfur and oxygen -2, nitrogen -3. And don't forget about this aluminum here. Aluminum is always +3. Then we have the transition metals, and the transition metals change according to whatever they're bonded with. They can have different ones. So copper can either be +1 or +2. It will be identified by the Roman numeral in the name. Try these. Again, pause this video, go through these things, get the answers. Alright, here are the answers. If you didn't pause it and do these things on your own, you're doing it wrong. Pause it and do it. Here we go. Tin 4-chloride. Since tin is a +4 charge, we have to have 4 chlorines, each one being -1. Iron 3 nitrite. Here's NO2 being the nitrite. So we have 3 of those to cancel out that +3 charge from iron. Ammonium oxide. Oxygen is -2. So we have 2 ammoniums to cancel out that charge. Chromium 2 phosphate. So chromium is a +2 charge. Phosphate is a -3 charge. Least common multiple between 2 and 3 is 6. So we end up with 3 different chromiums to get to +6, 2 different phosphates to get to -6. Finally, we have silver carbonate. Carbonate's -2, so we have 2 silvers. Potassium hydroxide. Platinum 4 perchlorate. Copper 1 iodate. Ammonium nitride. Notice it's IDE as in nitride, not nitrate. So we have just N with a -3 charge. We have to have 3 ammoniums to get there. Aluminum chloride, and then we have zinc oxide. Zinc is always +2. So that takes us all the way through the ionic compounds. Those are the difficult ones, in my opinion. Once we get to the covalent things, covalent compounds, they become much simpler. Naming them, these covalent. First of all, make sure you remember that you identify covalent molecules as compounds that have 2 nonmetals, or possibly 1 metalloid and 1 nonmetal. For example, silicon is that metalloid and is bonded to oxygen. If we have a metalloid and a nonmetal, it's also probably going to be covalent. We will name it as such anyway. And then we name them according to the prefixes. Have these memorized, 1 through 10. The ones that are kind of hard are the tetra, hepta, and nona, 4, 7, and 9. Most of the others, most individuals can memorize pretty easily. So again, make flashcards if you need, or practice counting in chemistry. You learn how to count in English when you're very, very little, maybe Spanish or French in middle school, and now you're counting in chemistry. Get 1 to 10. The less electronegative element of these things always gets listed first. Now, almost every single problem that you will get for these will be given to you in this format, where the least electronegative thing is listed first and also written first. But in case there is an issue, want to make sure that you understand that you can figure out which one has the least electronegativity, based on its proximity to fluorine. Fluorine is the most electronegative. Anything further away from fluorine is less. The first element only gets a prefix if there is 2 or more. And then the second element always gets a prefix. So if we're looking at the periodic table here, for the least electronegative, remember fluorine is the most. Then it would go like oxygen and chlorine would have almost the same. And then we'd keep going here. So it decreases electronegativity in this direction. So we have some to try. Remember that if there's only one of the first element, as in this case, no prefix is necessary. So this becomes sulfur dioxide. No matter what, we need a prefix for the second one. Even if there's only one of them, it still needs a prefix. So pause the video now and take some time, go through all of these. All right, welcome back. Here are the answers. Sulfur dioxide, silicon dioxide, so again, we have the prefixes. Tetraphosphorus decoxide. Now, there are some times when we drop a vowel, and it becomes pretty confusing when we should and when we shouldn't. So I will never count it wrong if you didn't drop the vowel. So this would be correct if you said decoxide or decaoxide. Nitrogen dioxide, dinitrogen dioxide. So here's that first example where we have, second example where we have a prefix for the first element because there's more than one of them. Carbon monoxide, because we have a single oxygen listed second. Iodine heptafluoride, and dinitrogen monoxide. Going the other way, the subscripts are told by the prefixes. That's all you need. And use subscripts to tell how many there are. So if you want to try these, so we have 1 sulfur, 6 fluorines because of hexa. Write it out that way. Pause and do the other 4. All right, welcome back. Here are the answers. Phosphorus trichloride is PF3. We have carbon tetrachloride, tetra is 4, so we have 4 chlorines. Boron triiodide, we have 3 iodines, so there's the iodide. And tetranitrogen hexoxide, so we have 6 oxygens. Finally, the acids. I'm going to simplify these as much as I possibly can. The prefix hydro only gets used for binary acids. Remember, binary means 2, so it's an acid made up of 2 elements and only 2 elements. Nothing more. Here they are: HF, HCl, HBr, HI, H2S. Those are the 5 that get a prefix. If it's not one of those 5, do not put hydro. But we have hydrofluoric, hydrochloric, hydrobromic, hydroiodic, and hydrosulfuric. Notice that the suffix for each of these, instead of getting changed to "ide," gets changed to "ic." So instead of hydrofluoride acid, it's hydrofluoric acid. Now the oxyacids, and these are the polyatomic ions that are in acids. So we have the different things like bromate, phosphate, iodate, sulfate, chromate, chlorate, carbonate. All of those things that end in "ate instead will become "ic" acid, so something like carbonic acid, iodic acid. Now, instead, if the ending ends in "ite," like nitrite, iodite, carbonite, it gets changed to "us." So it'd be nitrous acid, iodous acid, things like that. So try these acids, name them. Remember, you have to memorize this base molecule, so we end up with the correct chemical or the correct polyatomic ion that you're naming it after. Pause the video now, do these things, and practice them. No, I mean it. Pause it right now and do them on your own. All right, welcome back. So here are the answers. We have phosphate, so we have phosphoric acid. This and sulfur or sulfates are stem-changing compounds or stem-changing polyatomic. So instead of it being phosphic acid, it's phosphoric acid. Instead of being sulfus acid, it's sulfurous acid. So sulfurous acid because SO4 is sulfate, SO3 is sulfite. This thing here, CH3COO, is acetate, so it becomes acetic acid. HBr is one of the 5 that gets the prefix, so hydrobromic acid. And that's different than BrO3 because that is bromate. Bromine, bromate. So we have bromic acid. Finally, the perbromic acid, because we've added an oxygen. It still becomes perbromate, is the name of that polyatomic ion. So it's 8 becomes ic. The prefix still remains. Then we have carbonic acid. All right, going the other direction. Add hydrogens until the charge reaches 0. So it's really essential that you know the charges of those polyatomic ions. Hydrogens count as a positive 1 charge. So if we had sulfuric acid as our example, HSO4 is wrong because sulfate, SO4, is -2. Have to have 2 hydrogens, each one being positive 1, to get sulfuric acid correct, H2SO4. So again, another practice round. Try these. Pause it now. All right, welcome back. Here are the answers. Periodic acid. Iodic, or iodate, would be IO3. So periodate is IO4. So periodic acid becomes HIO4. And periodate is a -1 charge. Phosphoric acid is named after phosphate. Phosphate has a -3 charge, so we have to have 3 hydrogens there. Sulfuric acid, we did that one earlier. Hydrochloric acid, so this is one of the 5 hydros, so HCl, and that's different than chloric acid because chloric is named after chlorate, which is ClO3. But -1 charge, so 1 hydrogen. Oops. Perchlorate is ClO4, so perchloric acid is that. And nitrite is NO2, so nitrous acid is HNO2. So all of these things, the last 4, all have a -1 charge, so we just have 1 hydrogen accompanying them. We're almost done. That was acids. The last thing that we have to cover are these hydrates. I touched on that at the very beginning. So here we go again. The definition is an ionic compound that contains water molecules as an integrated part of the structure. This is also, you're familiar with these from the lab we just got done doing with the copper chloride hydrate molecule that you're trying to come up with the correct chemical formula for. So if we have some examples, that hydrate is signified by how many water molecules there are. So if there's 7 water molecules, we use the prefix hepta. So it becomes magnesium sulfate heptahydrate. Oops, typo. Hydrate. Cobalt chloride hexahydrate. Barium hydroxide octahydrate. I'm not sure if I said this or not. I want to make sure I go back. This is cobalt 2 chloride. Cobalt is a transition metal, so it needs that Roman numeral 2. So cobalt 2 hexahydrate. So there you go. That is how we name things. I would recommend going through this again and practicing those problems that come up at different times during the video and making sure you're able to do every single one of those. Also, I'll put up answers to the quiz. There'll be a link below this video so that you can see those, so you can see if you did them correctly. All right, questions? Feel free to see me before school or after school. Remember, before school is sometimes hit and miss. After school, I should always be free for at least a little while. So look forward to seeing some of you if you have questions. Otherwise, I hope this helped.